Okay, so let's continue with our lecture. So the next group of instruction will be the logic and arithmetic instruction, and this is very important in our microprocessor, in computer, or in any digital hardware. So it will involve the status flag where we have learned in chapter 2, and this 4-bit is very important in arithmetic operation, right? Because when we perform arithmetic, we want to know uh, the operation that we perform produce what type of result, whether it is negative number or whether it is zero, whether it has carry, whether it is overflow. So this information are important because the microprocessor, as we know, is a digital hardware, and digital hardware has limitation, right? Where uh, the size for storing the result is limited. For example, in our case, the size for storing the result is 32-bit. What if the result of arithmetic operation is more than 32-bit? So what is the the action to do? All right. So when we say that our system, our microprocessor is 32-bit, is that means the result cannot more than 32, right? So it can be more than 32-bit, but we need to have extra work. For example, we need two register to store the result that more than 32-bit, right? So if we have two register, we can store up to 64-bit already, but we need to know whether our result is more than that or not. If not more than that, we only need one register to store the result. If more than that, we need two register, and so on. All right, and also we need to know the result is whether positive or negative, especially when we perform the comparison. All right, so if we sub a number, for example a minus b, right? If the result is positive, means that a more than b. If the result is equal, means that if the result is 0, means that the number is equal. If the result is negative, means that the a is less than b. All right, so that information is provided in this bit or flags, right? So that is why we need to know what is uh, the operation or the time that uh, affect this flags. Uh, so let's look at the first arithmetic instruction, which is the add instruction, right? The add, which is the adder actually. Use the adder in our microprocessor, and of course the adder is in the ALU. And this is the instruction format where we have ADD, ADDS, all right. RD is the destination register with the OP2. OP2 is called an operand. Operand. So this operand can be a register or an immediate value, right? And the value is 8-bit immediate value. So for example, we want to add the content of R0 with immediate value 2, R0 plus 2. So the instruction will be ADDS R0, comma, hash, because hexadecimal is immediate value need to have hash and number 2, right? Or we can have format number 2 where we can have up to 3 operand. This we call operand. This is called opcode, right? So this is we call the source destination operand. This is the source operand, and we can have three operand where we have one destination and two source here. Here means that this one is registered, the second one here is the register, and this one can be register or immediate value. So in this instruction, we add this to this and store in this register, right? For example, this is R0, this is R1, this is R2. So we add R1 plus R2 and store in R0, right? And this is for you to know. The add instruction without the suffix s means that you use add only, no s here, does not update the flags. So remember, if you want to update these flags, your instruction must has this s. All right. So for example, we want to add the content of R0 to the content of R1, and the result is stored in R0. So the instruction is adds R0 R1. So when we execute the instruction, so we will have 4 plus 2, we have 6 in R0. And remember, this is destination, right? The result will be in R0, and R1, no change, right? And the operation, the size of the operation is always 32-bit, right? When you use add, means that you add 32-bit, 32-bit here plus 32-bit here. And when we want to add with the immediate value, right? So 4 we plus with 100, okay? So we will have 104 in the R0, okay? And one question for you. I said before this, the immediate value must be 8-bit, right? Here is 8-bit. But look at this number. Is it 8-bit? This is hexadecimal. Is it 8-bit?
No, doctor.
No, but this is wrong or correct? This instruction is can be wrong or correct. Yeah, in ARM microprocessor, because ARM microprocessor is very sophisticated. Although the instruction said that this one is not the value for the immediate value is 8-bit, right? But some of uh, number that is more than 8-bit can be used actually, because the microprocessor has a shifter that can produce the bigger number from an 8-bit number. For example, this number can be produced by shifter. Yeah, you can shift 8-bit value to get this value. All right, this is more than 8-bit definitely, but you can still use. But not all number you can generate. Uh, from an 8-bit, all right, using shift. There's a number that you cannot. For example, 1 2 3 4. That one you cannot. All right, but this one can be shifted. All right, so you need to be careful when you use the number that is more than 8-bit in assembly programming, especially for ARM microprocessor. Yeah, for other microprocessor, it is actually fixed. You don't have that feature. But ARM microprocessor, you have the they call it a pre-processing circuit, that it can generate the number for you, although sometimes it is not 8-bit, but it depends on the number that you use. All right, so in this case it is allowed. Okay, so uh, let's see the flags, the flags after the add instruction. So let's say, for example, the content of R0 is this, and the content of R1 is this. When we add R0 plus R1 and we store the result in R2, what the flags. What is N, what is Z, what is C, and V. So when we do the operation, this plus this, we have this, right? In R2. So N definitely equal to 1. Right? Because to check N, look at the MSB. So this 8 is 1000, means that MSB is 1. Right? So N is equal to 1. Or this indicate that the result is negative. Here, this is negative number in computer. Z is equal to 0 because the result is not 0. We have not 0, 0 result here. That's why Z equal to 0. If the result here all are 0, so we have Z equal to 1. But in this case, this is not 0, so Z equal to 0. C, when we plus this to this, there is no carry generated. So C equal to 0. V equal to 1. We have overflow here. All right, because this is actually out of 32-bit range for sign number already. Okay, so V equal to 1. So we have learned this in the design. And I want to show again here. Okay, and a very fast check is quite simple actually, whether we have overflow or not. Now, for example, when we look at this, this is a positive. This is a positive number, right? Because MSB is equal to 1. This also the positive, which is 1. So positive plus positive, you should have positive result, but your result is equal to but you get negative result, means that something is wrong. Something wrong here means that you have overflow actually, right? Or when we look at the add operation, I try to make it smaller instead of 32-bit. So let's make it smaller to 8-bit. Right, we have the number. Here is try to use 8-bit for should be 7F plus 1, right? Make it smaller. 7F plus 0, 1, right? And let's see whether we have overflow or not, right? So when we change this to binary, so we have 0, 1, 1, 1, 1, 1, 1, 1, and 0, 1, you have 0, 0, 0, 0, 0, 0, 0, 1. When you add the number, all right, so this you will have 0, 0, 0, 0, 0, 0, 0, 1. Of course, you don't have C equal to 0 because you don't have carry, right? And Z also equal to 0 because this one is not 0. But N, of course, equal to 1. V, now let's see this. When you change this to decimal, what is this value? This is positive, 1, 2, 7, and this is positive 1, right? When you add, you have actually positive 1 to 8, and this is actually more than 8-bit for sign number already, right? Because remember, for sign number 8-bit, you have between 1 minus 1 to 8 to positive 1 to 7, and you have the result 1 to 8, which is more than 1 to 7, and this overflow indicate that overflow equal to 1, right? Or you can check here. This is positive, right? Because MSB equal to 0. This one is positive because MSB equal to 0. But the result, negative. There is no way in the world, positive number plus positive number, you get negative result. So this is surely V equal to 1. Means that this result is not correct actually. Or not fit in 8-bit system, right? So this is 8-bit. So for 32-bit is actually the same, right? When you add these two numbers, you have this, okay? So V equal to 1, right? That is easiest way to check V. What about subtract? Yeah, subtract 32-bit number from a 32-bit number in destination register. Means that if this is the format 1, you have 2 operand. One is for the source operand, this is destination. So in this case, means that destination minus source, yeah, 32-bit, this minus this. Or format 2, where you have 3 operand, is that this one minus this one, and save the result in destination. Again, operand this, if you this one is immediate value, so it should be 8-bit value, or if more than 8-bit is must be a number that the hardware can generate from shift operation. And also the when we look at the ARM architecture, there is not shift, there is what they call a duplicate or operation. So there is two type of operation to generate the more than 8-bit of immediate value. If you write the value here more than 8-bit, but if that value cannot be generated by that operation, it will give you error. Okay, let's look at this example. So sub R0 R1, and remember R0 minus R1, and the result will be in R0. So in this case, R0 we have 4 minus 2, so we have 2 in R0 in this case, right? And let's see the flags. How to determine this flags? Yeah, so you can have n equal to 0 very easily, because yes, n equal to 0. Z equal to 0, yes, because this is not positive, not 0. C equal to 1. How to determine C equal to 1 and V equal to 0? These two is a little bit tricky, but to determine this, we need to have a little bit knowledge on how the hardware, the computer hardware or microprocessor hardware works actually. This is again related to what we have learned in digital design. So again, if I change this value to 8-bit, all right, we have 4 minus 2. Okay, so in microprocessor, remember the subtract operation is actually using the adder, the add, right? So what the computer do is actually do this for plus using the adder, and of course this one is complement to complement number, right? So what we do is actually this. For 8-bit is 0 0 0 0 0 1 0 0 is for number 4. What is minus 2? And remember we use plus. Minus 2 is in 8-bit is FE, right? You use calculator to get this. So you have 1 1 1 1 1 1 1 0 FE, and you add. So this one you add, you have 0. This one you have 1. This one you have 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. And this is actually carry. And you see the result for 8-bit is 0 in hexa 2, or simply number 2. 4 minus 2 is 2. And this is carry. You have carry. Do you have overflow? No, you don't have overflow because uh, 4 minus 2 can be positive or negative, right? So this one, and also 2 is within the range of the 8-bit, because remember the range for 8-bit is minus 1 to 8 to 1 to 7. So 2 is definitely in the range. So v equal to 1. This is the same with this one, right? That's why we have c equal to 1 here and v equal to 0. And we can test here using the software. Okay, so we can have here, and let's, for example, we want to run this this one we don't want anymore. Okay, we can comment that one. And for example, our program is to move, we use R0. Is it R0? Yes, R0 we have 4 and R1 we have 2. R0 we have 4. R1 we have 2. And we do the sub S, remember. If you don't have S, it will not affect the flags. I will show later. Part 1. And let's see the result when we execute this program. Right, we compile, no error. Run the simulation or run the debug. And let's run the program until here. All right. So just run, and we see R0 we have 2. Yes, for 4 minus 2 we have 2, but look at the flags. Yes, we have c equal to 1, n equal to 0, z equal to 0, v equal to 0. Right? So this floor 4 is exactly what we have here. Now let's look what is the result if we don't have this s. Right? We can use write the program this way, but remember, if we do this, the status flag will not be updated. Okay. So again, run. This is the program, and we will run all this. Run. We have 2, and let's look at the flags. Yeah, we don't have any updated flag, right? Not affected the flag. So C still remain 0. So remember, normally when we use arithmetic operation, we need this information. Yes? But sometimes we don't need. For example, we want to add a simple number, that this one is not needed. Okay. Next is the multiplication. Right. So we have multiplication here, MUL, where we multiply this to this. The source, we have 2 source operand. This multiplied to this, and the result will be in 32-bit RD destination. And the result here is 32-bit. We multiply 32-bit, the result is the 32-bit. And remember, normally in multiplication, most of the time the result is double of the operand. For example, if you multiply 4-bit number with a 4-bit number, if the number is big, so the result normally more than 4-bit. So the ARM microprocessor has another features that you can have 64-bit result, where the format is like this. For sign multiplication, we have this this multiplied by this, the source, and these two will be the result of the multiplication, right? And these two are 64-bit result. So for example, when we want to multiply here 0, and let's say the number is big. What is the number? Okay. Remember, if we have 8 32-bit, we need to use move and have a double move, right? And we want to, for example, this one is in odd 1, 1 2 3 4, and this one is SMULL, right? Multiply, and the result we want to save at R3 and R4, right? These two will be used to save the result for the multiplication. These are R0 and R1. So let's compile, and we don't have any error. And let's see the result when we run here. And this is the result. There is not more than 32-bit actually. If more than 32-bit, it need to be in here also, R3 and R4. Let's have another change a little bit so that the result is big, right? So because we have W here, no, we should have T, right? That is the mistake. Okay, do again. Okay, so run until here. Now we have more than 32-bit result. If you can see here, R3 and R4 is used for the result, where this is the right hand side 32-bit, which is the what we call the low part, the lowest 32-bit, and this is the highest 32-bit. The result will be in these two register. All right, this is high, this is low, high, low, 32-bit, 32-bit, right? So this is sign multiplication, and this is UMULL is unsigned multiplication, right? Very straightforward. And for the multiplication, there is no condition flag is affected. Condition flag affected for sub and add only. For division, we have this as div, which is the signed division. This is unsigned division. So this will perform the division. This divide this and store in destination, right? So for example, we have two operand here. if two operand like this, you can still use two operand. This divide this, and the result is in R0. So this one divide by this one. What is this value? This is of course the negative value. Yeah, this is actually minus 10. Stored in 2's complement number in microprocessor in R0. So minus 10 we divide by 2, right? So we have minus 5 in R0. So this is actually minus 5, right? The result. And for example, under unsigned, so A is 10 divided by 2. So we have 5 in R0. Okay, so that will be arithmetic instruction. And I think the last part for today, we are at 10:32, which is the logic instruction. So these are the logic instruction that we can perform in this microprocessor. The first one is AND, this one is OR, this one is XOR, and this one is AND also, but AND with the complement operand. This one is OR also, but OR with the complement operand. So we will look at the first three first because this is easy, right? So let's say, for example, we want to AND the value in R1 and R2, R1 and R2, and we store the result in R0. So when we want to AND these two, R1 and R2, so we actually need to AND bit by bit, right? So we can have here, in this case is 1, 2, 3, 4 with FF00. So we have that 2. So we have in hexa 1, 2, 3, 4 with 0, 0. Oh, is it FF00? Yeah, FF00. So 1 through 2, 3, 4 in binary is 0, 0, 0, 1. 2 is 0, 0, 1, 0. 3 is 0, 0, 1, 1. And 4 is 0, 1, 0, 0. F is 1, 1, 1, 1. Another F is same, and 0, very easy, and you end. So the end is straightforward. 0, yeah, 0 end with 1, you have 0. Anything end with 0, you will get 0. 1 end with 1, you will have 1. 0, 0, 1, 0. And all, because you end with 0 here, so all will be 0. So what you get here is 1, 2, 0, 0. So 1, 2, 0, 0 in the end, right? So you will get 1, 2, 0, 0 in this, right? So the conclusion is that when you want to, or observation, we can say that observation is that when we end anything end with FF or 1, we will preserve that value, and anything when we end with 0, it will become 0. So in this case, this one is preserved, this one is 0, 0, 1, 2, 0, 0, right? So AND operation is important in preserving the bit, or we want to do masking later on, right? We will see in the example in maybe next week what is the application, where to apply the AND operation. Normally we use for masking operation. For example, we want to preserve these two, but this one we want to clear off, yeah, so we can use AND, because anything end with 1, we get the value back, and anything with end with 0, we will reset to 0. So this operation is AND with the complement value of R2. All right. So a little bit different here. So we need to complement this value, right? So to complement this value, we can have this. This will be 0, 0, 0, 0, 0, 0, 0, 0. This will be 1, 1, 1, 1, 1, 1, 1, 1, yeah? Remember, we complement all this to this, this to this, this to this, this to this, and we all, and we end. So now we end these two. We will have, this one is 0, 0, 0, 1. We end, yeah? So we have 0, 0, 0, 0, 0, 0, 0, 1, 1, and 0, 1, 0, 0. So we will have 0, 0, 3, 4, definitely. 0, 0, 3, 4, yes. So we end this R1 with the complement value of this in R2. Okay, so BIC. For the other operation, so you can try on your own, right? And I think that's it. Shift and rotate operation, or maybe we can finish this all so that next week we can go to the program flow just a little bit more. All right, we have another 20 minutes. So let's complete this. The last part, the last group for today, shift and rotate instruction. Right, so this is very important in microprocessor. Shift, shifting the bit, whether you want to shift from the left to right or from the right to left. Okay, so the first one is called the ASR, or arithmetic shift right. L is logical shift left. This is logical shift right. This is rotate right. This is rotate right with extend. And the format is this. You can have up to 3 operand, right? So means that the value that you want to shift is in the here, and shift for how many bits, how many bits is here, and the result will be here. So this is the operation, logical shift left. You shift the left, the content of register, and of course when you shift to the left, you will left the MSB with empty value. So what is the value that you need to put in the MSB when you shift the value from the right to the left? All right, so that value is replaced by 0. When you shift first time, first one bit to the left, so MSB will get 0. When you shift again, MSB will get 0, and the previous bit will be shifted to the left. And again, at the this is this is LSB, the LSB, and at the MSB, the bit that is shifted out from the MSB will be copied to the C flags, the carry flags in the status register, right? So that is the operation of logical shift left. What about logical shift right? So the operation is actually opposite to logical shift left, where when you shift the bit from the left to the right, of course this one will be shifted to the next, and 0 will replace the bit in the MSB. And for the LSB, it will shifted out, and the value that is shifted out is copied in the carry flag. That is the logical shift right. What about rotate? So this is rotate right, rotate right. Rotate is just like rotate the bit. Actually, it is a shift operation also, but the difference is that in the shift, this one will go out and replace here with 0, but this one in rotate, the one that is shifted out here will be fed back into MSB here. All right, and also the one that shifted out is copied to the C flag, right? So that will be the rotate right. The rotate left, arithmetic shift right is similar to this. The only difference is that instead of replacing this with 0, when you shift to the right, it is copied the bit at the MSB. So for example, if MSB is initially 0, when you shift, this 0 will go to the next one, but this one will be remain 0 because it is copied and stay here. But if this one is 1, when you shift to the right, so the 1 here will go to the right, and this one is still 1 because it is copied to here. All right, it is always 1. If this is 0, it is always 0. And the one that shifted out is again copied to C, right? And the last one is rotate right with extend, with extended, right? This one is actually similar to this rotate right. The difference is that is rotate, the one that is shifted out is not immediately go to the MSB here, but it will go to C first before it go back to MSB. So that is the difference between these two. Okay, so let's look at the very simple example here. So for example, we want to shift the content of art1 to the left, right, 4 bit. Right? This means that we want to shift 4 times or 4 bit to the left. So R1 is this. So when you shift, you will have this. And of course, the result is saved in R0, right? So when you shift 4 bit from this, you will get this. Okay, very easy. And of course, the value inside C is still 0, right? Because you shift 0 out here and we store in C. Okay, what about arithmetic shift right? We shift the content of art1, which is this, to the right based on what is inside R2. So R2 is 4, means that we shift 4 bit also, 4 times, 4 times to the right. So what happened is that we will have the result in R0. So we will have FF05. Here, F05, we have the result to be FF05. How is that possible? So again, let's look at this. So we have F05, right? We have F05. So F in binary is 1, 1, 1, 1, 0 is 0, 0, 0, 0, 5 is 0, 1, 0, 1. And remember, this is MSB. When you shift 1 time, you will have, and again, MSB is copied because this is arithmetic shift right. So here, the value is still 1, and this one is actually shifted here, and this one is shifted here. So you have 0, 0, 0, 0, 0, 0, 1, 0, 1. Right, shift to the next. So this is one time. Second time you will have 1, 1, 1, 1 also, 1, 1 here, 0, 0, 0, 0, 0, 1, 0, 1. Third time you have 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0, 1, 0, 1. And the last shift you will have 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0, 1, 0, 1. Right? So this will be F, this will be F, this will be 0, this will be 5. So that's why you have FF05 in R0 here, FF05. Right? That is how the arithmetic shift right work. Okay, so I think for today, we will stop here and we will continue with program flow control and look at some example of writing, how to write the full program using what we have learned today and also next week to have a complete program for our microprocessor. Okay, so for today, I think we will stop here. So any question you can ask now, or maybe you can ask through Telegram.